A question to which I'm sure you want to know the answer to. What causes magnetism? To answer that question, we need to know that the source of all magnetism is moving charges, and that every charge that moves generates a magnetic field that completely fills the space around it. And it is the magnetic field that is the mechanism through which magnetic force is communicated between moving charge particles. Well, just like electric fields can be modeled with electric field lines, magnetic fields can also be modeled with magnetic field lines. Magnetic field lines form concentric circles centered around the charge's line of motion. In this sketch right here, this is depicting a charge, a positive charge that is moving directly away from you into the screen. And notice the orientation of the magnetic field lines is clockwise and centered around the line at which that charge is moving. Since that charge is moving directly away from us, the concentric circles are centered about that charge. Now, if you look at the magnetic field line, at each point, there's a magnetic field vector that is tangent to the magnetic field line at that point. And the magnetic field strength is stronger where the field lines are closer and weaker the farther away from the charge. So let's take a look at this. The source of all magnetism is moving charge. So let's take a positive charge that is moving in space. We'll say that this positive charge is moving with a velocity indicated by this vector. Let's indicate the line on which this velocity lies. So we're going to call this the line of motion or the line of velocity. Because this positive charge is moving in space, it is going to generate magnetic field completely surrounding the space around it. So the magnetic field would form concentric circles around this positive charge. So in this situation, since the velocity is moving diagonally up and to the right, the magnetic field lines will form these concentric circles with the orientation that I'm indicating in the picture. Now, the magnetic field isn't just centered around that positive charge. It's centered around the line of motion everywhere ahead of and behind this positive charge. So, for example, there is a magnetic field due to the positive charge right there where I just drew that circle. And the magnetic field lines surround that line of velocity at that point with the orientation that I'm indicating. Even way up here, there's a magnetic field lines completely surrounding the line of velocity. And behind this positive charge, there are magnetic field lines forming concentric circles around the line of velocity. So the magnetic field really extends everywhere in space surrounding the line of velocity of this charge. Now, I can't draw every possible magnetic field line for this charge, so this is just a representation. These magnetic field lines is a model that we use to indicate the magnitude and direction of the magnetic field at any point. So if we were to look at this positive charge, and let's say we are going to look down this line of velocity as if the positive charge is coming straight towards us. So if the positive charge is coming straight for us, the line of velocity is right in the center of that particle. And magnetic field lines form concentric circles around that particle's line of velocity. And in this situation, the magnetic field line's orientation will be counterclockwise as it's facing us. Now you're probably wondering, how do we determine the orientation of the magnetic field lines? Well, how we determine the orientation of the magnetic field lines is through one version of the right-hand rule. I'll call this version of the right-hand rule number 1, but the numbering doesn't really matter. So let's look at the right-hand rule. So this version of the right-hand rule we're going to use when we have moving charges. It allows us to find the direction of the magnetic field lines generated by those moving charges. And to do that, the first thing we have to do is take our right hand and take the thumb of our right hand and point it in the direction of the charge's velocity. Once we do that, we then will curl the fingers of our right hand around the line of velocity to form a circle. Now, the fingers of our right hand in forming that circle, it points in the direction of the magnetic field lines around the charge. So in other words, it gives us the orientation of the magnetic field surrounding the line of velocity of our charge. So looking at it in this picture, well, let's take our right hand, and I'll just draw our right hand right here. Here is the thumb of our right hand, and our right hand is curling around the line on which the charge is moving. So there's our right hand. And notice, that's a long thumbnail right there, but notice how our fingers are curling around that line of velocity. And that our fingers curling in that direction is indicating the orientation of the magnetic field lines. Well, let's look at this from a different vantage point. So let's say we have a positive charge, and this positive charge is moving straight up. Since the positive charge is moving straight up, the line of velocity is also straight up. Let's take our right hand and let's take our fingers and curl it around the line of velocity. So notice our fingers are curling in such a way to indicate the orientation of the magnetic field lines. So if we were to draw this, we would see that the magnetic field lines form concentric circles following the orientation of our fingers around the line of velocity. And if we were to look straight down on this, as if the charge is coming right towards us, that image would look like this over here that we drew. Well, now that we know how to determine the orientation of the magnetic field line surrounding our moving charges, we probably would want to know how to determine the magnetic field at a point. So our next video will talk about how to calculate the magnetic field due to a moving charge.